Hi, and welcome to our fourth installment in our series on mixing C++ and Rust. If you missed the previous episodes, I really recommend you check them out from the links in the video description. In this video, we will build on top of what we learned in the previous videos, and we'll be using almost every feature we discussed in the previous ones. The goal for today is to build a totally new UI application that goes beyond a simple hello world. Instead, we will build a small to-do application that lists open to-dos and allows us to mark them as done. In the end, we should have an app like this. Here, we just have our small window where we can add new to-dos. So, for example, to subscribe to the KDAP YouTube channel that we can then add, and we'll see that here our list actually updates, and we can even scroll this list. So if we added a bunch of different values, right, we could still see all of them. And of course, we should be able to also mark notes as done, which in this case will even move them to the bottom so that the unmarked ones are at the very top. And we can of course also unmark them. This UI may look simple, but it includes one of the most fundamental principles of UI programming, which is to expose structured data from the backend to the front end. In this case, a simple list of to-do items. However, the same principle applies when building UIs for tree structures, tables, and any other complex data structure. So learning this will make it possible to build very complex Qt applications with the Rust backend. So let's get started. The key to exposing structured data to Qt is to subclass the QAbstractItemModel class. In this tutorial, we will use CXX-Qt to define a QAbstractList model in Rust. The list model, in comparison to the item model, already implements some boilerplate for us, but the same principles apply for the item model as well. These abstract classes define the interface that Qt uses to reason about structured data. In the case of a list, we let Qt know how long our list is, and Qt will then, for each individual item, ask for the value in each row through the data function. For better QML compatibility, we will also define roles, which let us return multiple values per data point. In our case, this is first the name of the to-do, and second, whether it's already done. Now, with the plan that we have, let's get to coding. Because now we actually don't need any of the previous code, we can go ahead and initiate a completely new cargo project. So we'll go ahead and run cargo new. And within our app, we will first make sure that our cargo toml is set up correctly. The name's already set up correctly for us by cargo new. And then we'll add our dependencies, which are going to be the same dependencies that we used last time. So CXX, which is necessary because that's the code CXX-Qt generates. Then of course we'll need CXX-Qt itself. Again, I recommend you look up the currently stable version. I will use the Git version for now so that we have the very latest changes, but for production I wouldn't really recommend this. Then again, CXX-Qt lib with the full feature set, but again, for your application, look up what feature set you really need to speed up build times. And then talking about building, we'll also need the build dependency, which is CXX-Qt build. So that's it for our basic cargo toml setup. Now, in this video, I'll also show you how to structure your project a bit more cleanly. So here we, in our source directory, create a new file, which we'll call the to-do list. Then from our main.rs file, we need to declare this to-do list as a module so that, first of all, Rust Analyzer doesn't complain anymore that this file isn't in the source directory. It should then pick it up. Within this to-do list file, we can then start adding our CXX-Qt bridge. Like I said in the previous video, I really recommend you name this module QObject so that references to anything that lives inside this bridge are more obvious. Okay, so that now that Rust Analyzer has built our dependencies and has started figuring out that this module actually belongs to our project, we can then start defining our QObject. Again, our QObject will be backed by a Rust struct. So we'll first start by creating this Rust struct. In our case, this should be a list of to-dos. And what does each to-do need? Well, it needs a Boolean value, whether it has been done already or not, and then also a string, or in our case, we'll directly use QString to describe the actual to-do itself. Also, remember to make this type public, as we will expose it through the bridge later anyway. For our list of to-dos, we can simply use any Rust type we want. We're not limited to an internal structure here. This is one of the big advantages of using QAbstractList or item models, because they're agnostic to the internal data structure. And again, we'll use QString from cxxQlib, and my IDE has auto-imported this for me right here. Now, the next thing that I already mentioned in the previous video is that our Rust types that we want to wrap as a QObject should ideally implement the default trait, which is the easiest way to get them compatible with cxxQt and later QML, so that QML knows how to instantiate them. So I'll just go ahead and add that implementation. One thing I'll do here is when I initialize the to-dos, I'll already provide 2 example to-dos, so we later have something to look at in our initial UI, especially when we want to test it first before we start to actually modify any content. You'll also notice here that I'm using .into after the string literal, which will automatically convert our string literal into a QString. And we could also, of course, use QString from, which would do the same thing. And here I've already marked our tutorial video as done by setting the Boolean to true, because we're kind of already in the process of filming this, so once we get this app to start, we're basically done. And of course, I still need to upload to YouTube afterwards, so this will remain as false for now. Now that we've declared our internal Rust type, we can start exposing it through our bridge. Before we get to actually defining the QObject, let's get some of the imports out of the way. Like we did it in the previous tutorial, we'll just use normal CXX here. So we'll just use a normal extern C++ block, and we don't actually need to use any cxxQt features for this. This is pure CXX. As I said, we want to later inherit from the QAbstractList model type. This type we also need to declare in our bridge. For this, we will use a slightly different syntax to include the header file. QAbstractListModel is actually not included in cxxQlib, and you don't need this really, as we'll see later. But that just means we need to include the normal Qt header for it, which usually you do by using these kind of crocodiles or whatever you want to call them, this kind of parentheses to force the include in C++, and that will basically generate this in C++ then, right? So that's kind of the difference if you use the crocodiles in the include here, they'll also end up on the C++ side. And remember, we're in CXX land. This include is not Rust's include macro, this is the CXX specific one. We can then also simply declare the type to be an opaque type that's coming from the C++ side, because we've already imported the accompanying header. We'll then also need some types from cxxQlib. With the power of hindsight, I can already tell you which ones that are. So let me just add the imports for those really quick, and they just follow the usual pattern of including the header from cxxQlib and then redeclaring the type. So now we have QModel index, QVariant, and QString available. The next type we'll also need is QHash. I'll later show you in more detail why specifically, but especially if you're coming from Rust, QHash may be a bit confusing because it actually refers to a hash map. So it's an associative container going from one value to another. And the syntax for how to import this from cxxcute lib is slightly peculiar, so just stick with me and I'll explain this in a second. So here we actually can see that in cxxcute lib, the QHash, even though it's an associative container, doesn't actually take two type arguments. It only takes one. That is due to some limitations of Rust's orphan rules. And the way we get around this is that we can use a QHash pair, which is already typed by two specific types. So in our case, i32 and qbytearray. So the resulting QHash container that we'll get is an associative container between i32 and qbytearray, which is exactly what we'll need for the role names function that we will go through later. And you'll also notice that then when we use this in our bridge, this is actually a single type. This is no longer a generic type. And this is for the reason that we need to be explicit when we deal with C++ and Rust interop, which templated types we need. We unfortunately cannot rely on normal generic interaction. That is not yet possible between C++ and Rust without this workaround of specifying exactly which types you need. Now that we have the imports, we can start actually defining our QObject type. Now, again, this will start using cxxcute features. So we need to use rustqt and not just the extern Rust. Again, we'll start by creating a QObject type that we also want to expose as a QML element. In this case, we actually don't need any properties because the to-dos themselves aren't single data points, right? They are a whole list of data points, and a QProperty is really meant more to represent a single data point. So here we don't actually need any QProperties. What we do need is to be able to specify a base class. Because Qt actually relies on inheritance to implement these models, we need to be able to inherit from the right class, which in our case is the QAbstractList model. So we just tell cxxcute to use QAbstractList model as our base class. And then we can define our to-do list type as a wrapper around the outer to-do list Rust type. I'll also now start already declaring some of the functions that we'll need to implement later. And this mostly means we need to override existing functions from the base class, as that is how QAbstractList model works. If you haven't yet written up on the documentation of QAbstractList model, I highly recommend you do so. We will link it in the description, and it just goes through all the details on how this works on the C++ side, and we will basically apply the same concepts here. So the concepts are the same, the syntax will just be slightly different. And first of all, we, like I said, need to tell Qt how many rows are in our list. Only after Qt knows that, it will try to access the data through the data function. So we first need to override the row count function. Of course, that function needs to be implemented on the to-do list, so this is just normal CXX syntax here. And for kind of reasons that are more about QAbstract item model and that don't really make too much sense in a list model, this function also takes a parent, which we'll largely ignore going further. And this then returns an i32. Now, like I said, this function we want to override from the base class. And in C++, we would do that with the override keyword. In cxxcute, we actually have the same feature by simply adding the cxx override attribute to our function. And there are also the same attributes for virtual and for final, which just map to their corresponding C++ keywords. We then also want to use a different Rust name, because in Rust, the convention is actually to use snake case. So we'll simply use that here. and override the camel case implementation of C++. We'll also see here that now CXXCute will start complaining that this function doesn't actually exist. There is no associated item named row count in our to-do list. That is, of course, because we haven't implemented this yet. But this is kind of on purpose. I wanted to first go and declare the functions that we need, and then later we can implement them. So don't worry about these errors for now. And like I said, the next part would be that Qt will query our data by the data function. So we also need to declare that function. And the data function in Qt actually takes two different arguments, which is one, the index, which is going to also be a QModel index, and the role, which is an integer. And it will return a Q variant. The last part that we need is we need to tell QML how our different roles, which is what this integer refers to, are mapped to names in the QML code. And for this, there is the role names function, which obviously tells Qt what the names of each role are. And again, we will override this function from the base class. And in this case, we'll also give it a Rust name. And then we can override it. And this is exactly where our QHash comes into play. The role names function doesn't take any parameters, but it just returns this associative container between i32, which is the index of the role that will then be given to the data function, to the name in QML. We'll also notice here that my IDE has actually made a mistake and it has added a use statement for the QModel index, which has just come here due to an auto-completion. So make sure to remove any such use statements that you didn't add yourself, because they're actually not valid in the CXX bridge. And like I said, now we only get the errors that the associated items cannot be found, which makes sense as we have not implemented them yet. Before we start implementing them, especially the role names function, we will want to make sure to get the right values for each role. And the best way is to add a QEnum that defines the different roles. So let's do that within our bridge. Remember that QEnums must belong to either a Q object or a Q namespace. And in our case, we'll just call this to-do roles, which is sort of the default way to do this with Qt, is to define an enum for these roles, and then you use the values from that enum in the role names function. So here, one of the roles would be the to-do itself, and its sort of doneness, so whether it's done or not. So now at this point, we should really get started on finally getting rid of those errors here and implementing the functions. Again, functions need to be implemented outside the bridge. The bridge is only what we use to expose these functions, or even types, between Rust and C++. So because we called our module QObject, we will implement these on QObject to-do list. Let's start with the row count function. Like I said, we've renamed it with the Rust name to use snake case convention like we use in Rust, so we need to use this name here when we implement it. With the parent QModel index, I've actually renamed it here to be _parent, which to Rust just means this variable isn't used, which is fine, because this is really something that we only need for tree models or more advanced nested data structures. So here we can then just access our to-dos, again by derefing into our internal to-do list Rust, which we can access immutable through the deref function, and then we just need to return the length. Unfortunately here there's a small incompatibility between Qt and Rust. Rust uses the usize type to talk about types of lengths of containers, but Qt always uses integers, so i32. So we just need to cast this, but this is not a problem in the very, very vast majority of cases. So unless you plan to, have more than 4 billion or so items, I think we should be good. And if you've got that long of a to-do list, I would advise not using the small to-do app. Okay, so that's our first function implemented. The next one will then be our data function, which is sort of the meat of our application. Here I'll actually name the index value or variable also index, because of course when we access the data, we will need to know the index of that data. So now I'll show you a small trick of how you can actually go from an integer like this to an enum. In Rust, this wouldn't really be possible, but because these enums are shared between C++ and Rust, they inherit the semantic from C++ that they can be created from and to an integer very easily, which in this case we will do by assigning the to-do roles with a wrapper of our previous role. So this again kind of shows how these enums are really structured and how they work in CXX. They're really just a small wrapper type around an internal integer. However, this wrapper type now makes it far easier and more semantically accurate to actually decide what to do. So we can match on this role, but only after we've actually accessed our internal data structure. So here we will access our to-dos at the given index. In this case, the row of the index. There's also a column, but that's really more relevant for tables or maybe even tree structures, depending on how you structure them. And also here, notice that again, Rust prefers using usize, Qt prefers using i32, so we need to convert them. But then we can access our to-dos at the given index, and we'll of course only need to access actual data when there is some to access. If there is not, we will simply use qvariant default. Now, I've also, at this point, not actually imported either qvariant or any of the other types, but we can actually do this also through our QObject module, because that will re-export all the types we've declared in there. So now we have accessed our data at our given row. We have converted our role from a simple integer to an actual enum-like type. Now let's match on the role and decide what data to return in each step. So if the role is the to-do, so basically asking what is the to-do that we want to display, we want to return our to-do itself, which in this case is a QString, and we want to convert it into a qvariant, which we can simply do by calling .into, or we could also do qvariant from. So this is very similar to converting a Rust string into a QString. And the same goes for our second role, which will be our done state. And then, because we're using a CXX-based enum, we again need to have a match arm that covers every other case. Because remember, we created our to-do roles instance from an integer through its wrapper field. And this may indeed be an invalid integer. Qt shouldn't give us such an invalid integer, but it may theoretically happen. So Rust forces us to do the safe thing and specifically tell us what to do about it. In this case, we just don't really care about it, and we'll just return an empty data point, which is kind of the best we can do in this case. The last step is now to then also tell Qt what the role names map to. Like what name in QML should map to what role in our model. And this is exactly where we return that Q hash of i32 Q byte array. Here we'll use Rust's default function because Q hash, of course, implements the default trait, so we just get an empty container that we can then modify to insert our key value pairs, which in this case are going to be, first of all, our to-do role, and of that to-do role, we'll take the representation because we need to convert it to an integer. And then here we need to insert a Q byte array, which we can also nicely construct from a Rust string, actually. And again, we'll convert it using .into. Then we'll do the same for the done state. And then finally, we'll return the hash itself. After we've implemented the role names function, now all our errors in our bridge clear up, apart from maybe some unused types that we'll need later. And this now means we're already ready to start adding our QML GUI. So this is very simple very similar to how we did it the last time. So we'll again add our main.qml file, and then we can start implementing. I'll put down the default imports again. And I'll also import our own QML module, which we'll again declare in a bit in our build script. And this time I'll name it com.kdab.todo, but of course feel free to choose any URI you want. We can then start creating our application window again. I've now also already instantiated our Q object, our to-do list, which will be the model for the item view we will, for the list view we will add later on. Before we can actually add our list view though, we should consider how we want each individual item to be represented in our list view. In our case, I would really just like to have a checkbox. But for this, I need to wrap it in a QML component so that our list view can reuse it later. So a component is sort of similar to creating a class in QML that it can be reused later. For list views and other kind of model views, usually these individual items are called delegates. So this is basically what the model delegates the display of a single item to. Our checkbox can then fill the whole list view's width by using a special list view.view.width attribute. And we will make sure to set the checked state of the checkbox to the doneness state of our model. This is exactly where those role names come in. So this done here is coming from our role names function. This is exactly that done state here. So if we were to choose any other name in the role names function, we would have to adjust it accordingly in QML. For the text of the checkbox, we will then use the to-do. Again, this is the role name coming from our Rust side. We can also set our font to strike out, so to basically strike through any text whenever our model is done. And that is basically all we need to describe the checkboxes that will be instantiated for each individual to-do item. At least for now. We will then add actually modifying the to-do state later. So for now, this will just be here to display the data we already have, and we will get back to actually adding new to-dos and setting the checked state in a bit. But now we're actually ready to implement our list view. we can actually, again, fill the whole window with this list view. And then we just need to add our model, which in this case is our to-do list, which we add by its ID. So this just means that the list view will access all the data through our to-do list object. We then also need to tell it what the delegate should be. So in this case, this is of course our checkbox component. And we'll also just, for this to look a bit nicer, we'll add a little spacing in between the individual items so they're not quite as clumped together. And with this QML code, our UI is already ready for its first test drive. So let's first of all actually use the build script that we used from the previous video. So I'll just copy that over. And then we can adapt our build script because it's basically the same as before. I've just used a different name for the URI of our QML module. So com.kdap.todo, not .tutorial. And then also here I've moved our bridge into this to-do list Rust file. So we'll also use that instead. But that basically covers our build script. We can then go back into our main Rust file. Then again, from cxecute lib, we'll want to use the QGUI application and the QQML application engine and QURL. And then instantiate everything accordingly. And remember, we've renamed our QML module, so we also need to change the path for our QURL, which is going to be Qt, QML, com, KDAP, and then to-do and not tutorial. And after that, remember to still add the path to our main.qml file, so qml/main.qml. And now we can try building this app and see whether it works. And again, the first compilation can take a bit of time, especially with cxecute lib, but remember you should only have to do this once, and after that it should automatically use the cached version. Perfect! This time without any errors that I need to fix. So here we have our first to-do list. And as you can see, this includes both items that we added in Rust. So we have successfully accessed the data from our model, from QML, through to the Rust backend via C++, and we're right where we want it to be. Of course, like I said, at this point, we haven't yet added any mutability of the data. So for example, if I click upload to YouTube, while the checkbox thinks it is checked, the fact that it's not striked out actually reveals to us that the data hasn't changed in the model. And if we click this a bunch of times, this won't change. And the same goes for unmarking the tutorial video. The data itself hasn't really changed, so our model.done will still return that this is done, which it is. It's just the checkbox that thinks that things have changed. So now let's get to fixing this. Let's get back into our application to start adding mutability. I'll go back into our to-do list module because the main function won't have to change. And then in this case, I'll add a new Rust Qt block, but you don't really need to do this. I will start adding the functions that we need to modify our data. The first one will be a QInvocable, which again means that we can access this function from QML. We will call it setChecked. And this setChecked function will first take a pin to a mutable reference of our to-do list. Pin is a bit of a complicated topic, but the basics of it is that in C++, the Q objects rely on the fact that they always live at the same memory address and aren't moved around in memory. Rust, however, usually expects types to be movable, which can lead to conflicts. And the pin type is there to resolve this. It basically tells Rust, hey, even though we have a mutable reference here, we shouldn't move anything that's inside here. So please keep this pinned in memory at a specific location. We will then also take the row and the Boolean value of whether our to-do was checked. And we don't have to return anything as we're actually mutating the state. But I also changed the Rust name so that, again, we adhere to the snake case conversion that is typical in Rust. The next part will be that we need to access certain protected functions from our base class. These are begin reset model and end reset model. These functions basically tell all the views that are attached to our model that our data is being reset, and they need to get all the data back from the model and forget everything that the model previously reported. If you wanted to implement this in the best way possible, you would probably not use reset model, but rather something like add data point or like begin insert rows, begin insert columns, and there's a bunch of associated methods that work similarly. But because this is a tutorial and we want to keep things short, I'll just use begin reset model. The same concepts apply, though, if you want to use the advanced techniques, but then please refer to the Qt documentation that will show you how to do this. And again, we'll give these functions the correct Rust names within snake case. And again, of course, our bridge will start complaining that the setCheck function isn't implemented yet. So let's just go ahead and start doing that. So here we can see how to access our data in a mutable way, going from our QObject down into the internal Rust struct. And this looks somewhat complicated, but once you get the hang of it, it's actually not that difficult. First of all, because we have our pin type here, which we actually need to import from the standard library, we also need to call asMut if we want to use our pin for multiple mutable function calls. This is just a peculiarity of how the pin type works, which is unfortunately out of our control as it's a standard library type. And after that, we can then call the rustmut function, which actually comes from the CXX type trait. So you may have to import this trait in order for this function to become available in your QObject type. But this is exactly the function that I meant when I said when you use an immutable dereference, you call .rust. If you want to make a mutable dereference, you call rustmut. And unfortunately, this time the compiler cannot take this away and do it automatically, at least not in the current version. So we need to call this as well. That will also mean that our self-reference will need to be mutable as well. So this is just some boilerplate that you'll quickly get used to, but it's something to kind of keep in mind, and we are working to find ways that we can maybe improve the situation, but this is just how pin data is represented in Rust and how that works. But now that we actually have a reference to our done state, we can first of all check whether we actually have anything that changed. And if indeed something changed, we can assign the new value. What I'm also going to do here is usually I would emit the data change signal, but what I want to do is I want items that were checked to move down in the list. So for this, I will just call the sort function, which doesn't exist yet. And this is also something I want to show you, is we don't necessarily need to expose all functions that are in our QObject to C++. So here we'll just go ahead and add a new sort function that doesn't exist at all in the C++ world, but is just a helper method for us on the Rust side. And here we will just call the begin reset model and end reset model functions, which tell Qt that in between the begin and the end, it shouldn't try and access the data, and that after the reset is done, it should requery all the data that was previously in any of the views, which, like I said, can be optimized further, but this is good enough for this tutorial today. And here we'll just use the sort by key function in order to sort our values, and this will then reset the data from our model. Oh, I'm also noticing that my language server is actually complaining because I forgot to dereference the done value here. Because it's a Boolean, we can simply copy it around and don't need to worry about lifetimes. So that should hopefully fix itself. Then the next part would be for us to actually allow us to add new to-dos as well. Now we can set them as done. So again, we'll go into our bridge and we'll declare our new function, which we, in this case, want to call add to do. Again, this needs to be Qt invocable and needs to have a Rust name. And here we can finally also use the Q string that our language server has always been complaining about that we haven't used yet. So this is where we need it. And then again, we need to implement the function. Here, when pushing into our to-dos list, we will insert a tuple where, of course, the done state is false, because, of course, when we add a new to-do, it's not yet done yet. And then we'll also clone the Q string. This is more or less standard C++ behavior because we don't actually get the Q string by value on the Rust side, or rather, it would also be the same on the C++ side. C++ default is just to pass references around, so this is the way to do it. And in this case, the cloning of the Q string doesn't really matter that much, especially as Q strings internally share their data. And then we, again, simply sort, which will also reset our model. Again, this is sort of cutting it a bit short. If you want to implement a really properly well done item model, you will probably want to add the appropriate calls to begin add rows and end insert rows respectively. But for this, just resetting is fine, is good enough. And with these few changes, we're already ready to go back into our QML and add the new UI elements. First of all, we will start adding a footer, which I'll just make a row layout for now, which will contain both a text field and a button to add our new to-do items. Here, our text field just needs an ID, so we can reference it later. It can also fill the whole width, because the more space we have here, the better. And then we'll also add a placeholder text so that people know what this text field is for. And then we can already start adding the button. So here we just call the add to do function that we just declared in Rust with the text that was entered into the new to do text field. So that means we can add the to-dos, and now we just need to change it so that clicking our checkbox actually checks off the to-do items in our model as well. For this, we can just use the onChecked changed signal that we can implement in QML. And here we just call the setChecked function with the index we're in right now and the new checked value. And with this, we should be able to run our application again and see that we should be able to both add new to-do items and also to check existing to-do items off our list, which should then also be sorted to the bottom. And here we go. Here's our final application. We can mark and unmark items, which in this case does not seem to work quite correctly. So let's go back and see where we went wrong. I think our problem here is that in this case, the model is not actually the right name here. We need to refer to our to-do list directly in order to call the setChecked function. Because otherwise, model will just mean the Q abstract item model itself and not our specific subclass. Okay, so let's try this again. And there we go. Now, when we check an item, it is both moves to the bottom and its actual checked value changes. So we also see this in the strike through value of that item. And we can also add new to-dos, like subscribing to the KDAB YouTube channel, which I'm sure all of you have already done, so we can probably mark this off the list as well. And we're also mostly done with filming our tutorial video, as this is already our final application. And with this simple to-do application, we now know most of what's required to build full-scale applications with Qt and Rust. We learned how to choose a base class with CXX-Qt, including how to override and inherit methods from it. We then combined these features to provide our own list of to-dos to QML. As I mentioned before, the same concepts apply to more complex data structures as well. So this would enable us to build far more complex applications as well. Combined with the features of CXX and CXX-Qt that we covered in the previous videos, we now have a good overview of how to integrate Rust with C++ as well as Qt. There's of course a lot more that we could cover, so let us know in the comments what part of Rust and C++ integration you would like to hear about. If you would like to go into detail on how to include Rust in your C++ application, you can reach out to KDAB directly about a workshop. Also, if you're interested to learn Rust programming, check out the Rust courses on KDAB's training website. The link is in the description. For questions around CXX-Qt, we'll also link documentation, our GitHub repository, and our Zulip chat in the description, which are all free resources. So for now, this means bye und bis zum nächsten Mal.